Hello everyone and welcome to the Math Science Wednesday. This the another episode in the series which exists and was planned and definitely is not happening because I learned something and I have to use it right now in my paper. So, what will we be doing today in the Math Science Wednesday, you may ask? Well, I'm sorry. I'm sorry, give me a second. I'm trying to sort of capture to show you my screen. Taking me a minute. So, alright. Just give me a second, right? Just might take a bit. Verify. Yes! Oh yes! Oh yes, it worked. Great. Google Docs, sign in. I should be signed in. I am signed in. Oh, amazing. So, today we will be obviously working on hyper-operational mathematics. The thought experiment, which I've bloody done, gone and made. So, started actually, not made. This is where we last ended, and yeah, I slept extremely well tonight. Definitely with no problems, because, you know, don't worry about it. So, anyway, which way should we operate? Not always equal to the from finding then exponents. So right now, let me just rewrite that because we will be doing it a bit differently. Right now, we have two ways to approach this problem. We do have two of them. And first one is to just turn exponents into a symmetric operation. Not easy, but there's also a second one which I really like. Proof that it is not unnatural for exponents to be asymmetric. We will we'll start with the second way because it might seem a bit easier if you are familiar with quaternions. Oh yeah, quaternions, let's go. Yes, quaternions. Now, what are quaternions? I'm so glad no one asked. Wikipedia, please. Great. Quaternions. Quaternions is not for sale. This Wednesday, before I visit Wikipedia past year, the value you got from it whenever you're able to give, if you can, 2% of readers who give, oh, that I do want to give. Everyone reading it, I just gave, we'd hit our goal in a couple of hours. No idea what this is, but I assume it's like $5. I can't really donate on stream because, you know, people steal my credit card number. I will donate after stream. So, here's the very important thing: quaternion multiplication table. This is awesome. I love this so much. Let me just take the wiki over here. Can I pin it somehow? Can I pin it? Can I pin Firefox? Okay, let me open up second Firefox. How to pin Firefox to your screen. Wait, can you not pin it like this one? Windows menu button in the taskbar, arrow next to all apps. From the taskbar, no. Taskbar, oh, these are all so unhelpful. No, never mind, we'll manage. So, let me just first get some music going. Some gaming music, there we go. That seems like real research music. Great. So quaternions, and I'm sorry, but this is just so awesome. I have to share it with you. If you are familiar with quaternions, this is a quaternion multiplication table. Yup, and insert table. Should I say that's from Wikipedia? Will be weird if I say that. I could just link Wikipedia here actually. And if I'm not mistaken, that's great, listening wiki, because that's my source. And the gamer source, if I do say so myself. So, this is a bit, would prefer to be a bit more square, but we'll manage. 1 J K quaternions. Why is J capital? It should not be. Quaternions. So let me move it all to the next page because that would seem, seems cleaner. Quaternions and multiplication. There we go. That's gaming. 1 I J K. 1 times 1 is equal to 1. I times I is equal to -1. J times J is equal to -1, and K times K is equal to -1. Now, it's I negative J, K, J, no, J, I, J, K, J, negative K, negative I. Multiplication symbol. Is it insert equation times? There we go. Should also format this a bit better. Like squares. Can I? Oh, I can make perfect squares. It's so upsetting. J K. Should be K here. Format options. No, oh fudge. Okay, it's upsetting, but I can live with that. This should be this right, like this. I can live with that. It's fine. There we go. Now, I should also I would prefer text to be on the right. Now, you may notice that based on this table, and this is the sick part. I love this part. All right, I love this. This is great. J times K. All right, J times K is equal to 1 I, and K times J is equal to -I. Isn't that sick? Which means that K times J is not equal and wasn't it NEQ or NQ or not E or NEQ or NQ or NE. K times J. This is absurd. This is absurd. This is really absurd. What that means is that that's insane. I have a theory and I want to test it. But for that, quaternions will not be enough. Oh, Let's do it. I am really excited. I promised myself to not research anything. I promised myself not to research anything, so octinions. Yes. Yeah, I know. We will. I will make. Don't worry. But here's what's so exciting about this. Something I'd like to check. Yeah, actually, what I'm saying right now, this is dumb probably. I will probably have to go through this entire thing. So, whoops. Yeah, Wait, what? If norm O implies the existence of inverses for every non-zero element of O. Yeah. I know. Okay. Commutative. That's the. It's not symmetrical. It's commutative. I'm an idiot. Symmetric. First of all, symmetric was the last one, not next one. To be non-commutative, I assume that would be word. Non-commutative. Quaternions. Now this is really fun. Is what that means. Do retain one property shared by RC and H. The norm on O satisfies. This equation means that the octanions form a composition algebra. Alright, so okay, at this point that's just insane. Of course they made a table! What's really funny about this is that these things do go on forever. When it comes to these imaginary numbers, they do go on forever, which could mean that if I could make a connection between imaginary numbers and operations that could suggest that there is different number of imaginary numbers per operation, which would be extremely fun. Alright. I will have to read, probably, I mean, definitely this one I will have to read, which is the longest, because quaternions are the most useful ones. Then I would have to read, possibly I'd have to read this, and if I'm feeling, if I'm feeling like it, I might read this. This is not actually that necessary. But quaternions, well, this might be a must-have, so, well. Time to fry my brain. Let's go.
All the roads we
quantity reduced by division of two numbers. No, sorry, not familiar with English. But I get stumped by what this means. One of them directly aligned. Wait, what? Oh, wait, Back One Day. I don't know if I should play Back One Day. It's a new song, relatively new. It's still new in my heart. Xenogenesis, there we go. Yeah, this, okay. Three-dimensional rotations, yeah. Because quaternions help you describe rotations in 3 dimensions. And can be used alongside. Right, we don't need history, although it could possibly be nice. They're all equal. That's interesting. That's useful to know, because I'm pretty sure octonions also should have this thing. Yes, all of these are negative. Yeah. They all have the same property, which means squaring them gives you a negative number. Could be useful. Just saying. And I'm also pretty certain that these are just quaternions. This is a quaternion square. So this is a quaternion. So if you go to sedenions, right? That, like this part is just octonions. These are quaternions, and these are complex numbers. These are real numbers. Can we go further than that, by the way? Construction. Yeah. So you can go however far you want, right? Yeah, produce a sequence of algebras over the field of real numbers, each with twice the dimension of previous one. Yeah, so you can go further if you want. How far can you go? Non-trivial zero. What? 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 Yes! I was right. The music is perfect for that. Music is perfect. I was right. With this, look at that. There is. Great. That's so great. You know why? We will have to read all of those. Non-trivial zero divisions. This funky. It's really funky. I don't like that because that means we are okay. But this is above. So this is okay. This is too much for my brain. But yeah, multiplication process. That's awesome. That is awesome. Also, that's awesome. That's just awesome. Okay, ordered. So chemical field operations of basic example. Okay, go. So, commutative. We already know that. We have to understand all of those to understand how they break. Power association. Binary is weak from us. Okay, alternative. Oh yes. Oh yes. That's why they break, because every single time you have more. Oh, that makes so much sense. I love this. But what's really interesting about this is that if you think of incrementation as working only on real numbers, addition as working on complex numbers, multiplication as working on quaternions, powers, exponentiation, obviously, I know I forgot such a simple word, I'm sorry, my brain is melting. Powers working as on octonions, well, that actually doesn't solve anything. Why is it a good step? I do believe that's a step in the right direction. First of all, First thing that we can notice is that none of these will get rid of commutative properties of addition. Addition works in the same way in all of them, which is already a good sign, considering that we are trying to create a field that is only dependent on addition. So that's a good sign, I would say. Now, when it comes to the rest, these are all multiplication properties, and multiplication, considering that is the first hyper operation in the field, then it will be important to understand. Alright. Yes, I have to understand the exact tomorrow comments, 0. One equation, 2 plus 3 plus 4, yes. Oh, parentheses were rearranged on each line, the other expressions were not altered. That also makes a lot of sense, considering, you know, how octanions work. Yes, you can see over here. It would make sense when you have this many, it's... yes, it makes sense. Yeah. Alright. This general overview for now, which multiplication need not be associative, only alternative. Yes, we're losing this property. This is further for all x and y in the algebra. Every associative algebra is obviously alternative, but there are some strictly non-associative algebras such as octanions. Yes, that's where we came from. In which associator is alternating. Okay, associated, I'm sorry. I'm tired, I'm really tired. I did make a whole video today, but let's carry on. Is a trilinear map given by xyz is equal to xyz minus xyz. By definition, a multilinear map is alternating. It vanishes whenever two of its arguments are equal. Okay. This together imply that... okay. Ever so slightly losing me here, but I think there's a couple of things I can catch on. Yeah, still. This equivalent of flexible identity. I mean, yeah, it makes... That's it. I mean, it does make sense, obviously it does. It's just that my small lizard brain might be having some troubles with this. So, Paint. I think whenever you have troubles in life, Paint always comes to the rescue. I will have to set up my graphical tablet. So just give me a second, because you know I think it still should be better than running one. Alright. Great graphical tablet works. So turn your map. As a function of several variables, okay, the linear is separated by in each variable function. Why such complex words for something that simple? I think I'm misunderstanding this. It can't be that simple, right? Multilinear map is a function of vector spaces, modules of the going view, already for each I, if of all of the variables but the I are held constant, then a function of the I. This as a linear combination of basis vector function variable. No, there goes my graph about it. Okay. I feel like I should say something. I don't know, I'm doing the research on stream. This is the top one not good idea. Is alternating if it vanishes whenever two of its arguments are equal. Yes, because trying a linear map. Let's okay, that just links the same thing. Never mind. Let's go straight for the multilinear map. This is very deceptive. I feel like or maybe my brain is smooth. There's also a possibility. V1. That's probably but that's for linear maps. On N matrices I trilinear function. Let's start. Oh, there goes back my graph. There goes away. Cool. Alright, let's do it in a simple way. Oh my goodness, you mind stopping that? Thank you. Multi-linear maps examples, please. Linear task indeed IK. I love it. Let's go for it. Some vectors may belong to different vector spaces and produce a vector as its output. Also, if you fix all but one of the input vectors, then the function is linear in the remaining input vector. Why the font is so funky? It's wow, it is not live. Oh, okay, there we go. Also, if you fix all but one of the input vectors, then the function is linear in the remaining input vector. Yeah, that, yes, okay. Only one input is called a linear map. Yes, and those that take two inputs are called bilinear. Yeah, and then trilinear makes sense. Most general form of multilinear map. Wow, we studied general. Well, this will be the ride. We shall work with the bilinear case. Never mind, that's okay. The general case is simpler. The answer is the most general form of. Give me a second. There we go. The answer is the most general form of bilinear map from RM. Is I feel like I'm going in circles. Any arbitrary vector. I get that. Let's why. I get what you are saying. I don't get exactly why. You are saying you need to buy on your map to see that this is the most form out of any binary map. That. Okay. I mean, but they are quite different. Let's have linear maps, maybe. Vector spaces or modules. I feel like it's really simple, but it's very technically defined here. Which I was talking something this simple then. Oh my goodness, this will be fun. Alright. VIL constant, then yeah, it's a linear function. Yes, great. Because then the rest are constant, makes sense. One variable is a linear map. Yep. And two variables are a linear map. Yes. Give me more sources, please. Because are used in most cases. However, according to Hammond, Grossman, and others, this presumption misses the complexity of considering the structures of pairs, triplets, and general multivectors. I think that's what I'm missing. Multilinear algebra, a multivector, sometimes called Clifford number, is an element of exterior algebra of a vector space. This algebra is graded, associative, and alternating. We already got that. I kind of, went from the end to the back, so yeah, we get that. Angles of linear combinations of simple k-vectors of non-decomposable k-vectors or k-blades of the form. A k-vector is such a linear combination that is only of degree k. All terms are k-blades for the same k. Yeah, this multivector may be either a k-vector of any element of exterior algebra, and depending on the author's definition of k-vector. In differential geometry, so exterior algebra will be. We're getting somewhere. Wait, no. I think we found it. I think this is the base for the rest. So based on this, we can get the multivector, from which we can get the multilinear algebra, from which we can get the multilinear map, from which we can get the alternative algebra. Yes, that's it. Okay, great. Well, let's go for it. This will be a light read. We don't cover all of this, but we do cover the basics. So, it's a real vector space with a basis containing a pair of unit vectors. Yes. That's familiar territory, very familiar. Yes. Suppose that V is equal to AB. Yes. Yes. Okay. Are a pair of given vectors in R. Should I say R to no. Real to well, that's written in components. It's a unique parallelogram having V and W as two of its sides. The area of this parallelogram is given by a standard determined formula. Okay, I might need paint here. There we go. So, oh boy, we are going. It's absolutely not. No, yeah, last time it went. There it is. I have no idea. Alright. So I get this. So V is equal to A and B. W would be equal in this case to C and D. Area, then area for, pardon my, terrible handwriting. This is deceptively simple. I don't like that because yeah, you just input those here. That is deceptively simple. That is deceptively simple. I don't know if... Yeah, and then... Yeah, okay. So we just get A, D minus B, C. The exterior product of B and W. That was... wait. Oh wait, that could make sense? Maybe? AD minus BC? The distributive law of the exterior product, that's... The way I'm guessing is, well, E will appear twice, so you just exterior product E multiplied by everything that was multiplied by exterior product. Nope, you E and it's no quite. Not quite. Right. So it's gonna be bumpy, right? Okay. Element of the matrix of this. Alright, I think I get that. So you have one vector, right? That's defined by A times this is just so that you wouldn't have numbers, only vectors. It's deceptively simple so far. Yeah, this is just normal stuff. So exterior product then would be... Wait, that's a bit more. That needs unpacking. A... Maybe double normally. A, D minus B, C E1 E2. And last uses the fact that exterior product is alternating. Okay, kind of using something that we are only trying to build up to, but fine, yeah, yep. And in particular negative. Okay. Exterior product, I take it back. Get it. Common definitions. Motivating because I need motivation. Motivation. Oh, that seems very familiar. Oh, this is exterior algebra. Oh, this is just links to itself. Formal definition. I put that. Okay, it's fine. It's fine. Algebra. One vector space V over a field K is defined as a tensor. All elements. Oh my goodness gracious. Okay, alright. The fact that the exterior product is alternating also forces E. Yeah, equal to 0. Yes. Okay. Minus all clockwise. I still don't really get what this exterior, what is the exterior product. I don't really get that. What's the point of it? That's, yeah, what's the... Wait, can I what? The cross product, blue vector, yes. In relation to the exterior product, light blue. This is exterior product. I mean, that's the... Cross product is length. The length of cross product is to the length of the parallel unit vector red, as the size of the exterior product is size. The exterior product, light blue parallelogram, yes. The length of the cross product is to the length of the parallel unit vector, as the size of the exterior product is to the size of the reference parallelogram. This is the exterior product then. This. That's it. This is the... What's the difference between these two then? And why do we in this one still have the... I'm so mind blown right now. Cannot we then say... Wait, so what's the difference between area and the exterior product of V and W? I don't... It's mind-blowing. It is mind-blowing. Exterior algebras comes with the cross product. Yeah, that's simple. Yeah, but... No, wait! No, wait! Oh, wait now! No, wait now! Oh, wait now! Oh, wait now! Oh, wait now! Oh, wait now! Wait. Should we wait now? I'm starting to get an understanding, because this works, but this is A, B, yeah, so this should be also this. If you consider this to be the A vector, this to be B vector, then A exterior product B should be inside. Mind blown! I guess. But then there will be no need for this. Because this is... it's a 3 dimensions, to be fair. But still, over here we end up with this. I don't see the point in exterior product existing. Which is concerning, because if you don't see a point in something in math existing, that most of the time means that the problem is with you, because you don't see it. Oh, they are then 3. Fine. Let's go. Let's go for it. 3 vectors. What would that even mean? Oh, because in here we have 2 3-dimensional vectors, and here we have 3 3-dimensional. So 2 3-dimensional vectors and 3 3-dimensional vectors. Oh, maybe that's the difference. Is it? It's maybe so. So the exterior product then is a generalized version of the area, generalized over all dimensions and all numbers of vectors. One-dimensional space. I swear. I still don't understand. Yeah, because this is by itself, so it's equal to 0. Because this is equal to x, so 0 plus this plus y, which means this is equal to this in negative, which we, yes, that's true. But okay, it's this, yes, that's true already. That's right. Okay. I just have to. This. Oh boy. I still have no idea what the x. I just still don't get it. This zero product. This is multiplication, but more powerful, less powerful, different. I have no idea. Exterior product. Yeah. No. Yes, so it's a generalized form, right? I think. By the way, I'm using multiplication as cross product all the time, because if you do \times in LaTeX, then that's what that symbol get. Geometrically, the cross product refers to the area 1 by power. Yes. So yeah, this is just generalized version. That's true. Yes, great, fantastic. Oh, it's so amazing, so cool, so neat. Okay, what can we do better? I mean, this always sounds to me like Apex Team. I don't know why. Anyway. Basic directives, yes. But why we? Oh, we are left with this. I think I get it. Oh, but I barely get it. I think I get it. I'm pretty certain. Let's check an example. Right? I think I get it. Exterior product, because exterior product would be just the generalized version of the area over for all of the different shapes and sizes of vectors. Yeah. Oh boy, oh, this is fun. I like it. All right. This is rabbit hole and a half. I was supposed to do shorts right now. I was supposed to work on a couple of shorts, but I got excited by the octanions add to. A third vector. Okay, so formal definitions, that's what we need right now. Yes. Alright. 0 is equal to this. Great, hence, yep. But when you have this in brackets, then xx, xy, yx, yy. That's so it just distributes normally? Does it now? If it distributes normally, then we go back to this example, right? Then would be equal to I don't know if I mean, I never trust myself to do it. So this would be, yeah, because all these are just multiplied by the appropriate vector. So this would be a e1 or 0 actually, 0 as b e1. This c e0 plus b e1. Which would then mean that this will be... Oh, this is a question mark, alright? Just big red question mark. I have no idea how any of this works. I'm just trying to figure out. So, then... distribute. A is 0, this is 0. So, then what we would have is... A is 0... C is 0... plus... A E0. I feel like I need colors for this. Sorry to be the 5-year-old in the room, but I will need colors for this. Actually, get this right. Then CE0. Yes, plus. There we go. AE0, then this DE1, obviously it's DE1, DE. Then plus BE1 extra product. Oh, come on. I'm doing it really quickly, I know. But I'm trying to just understand. This is how it distributes, right? It distributes normally. But I don't think it distributes normally. E1. It was weird. It don't distribute normally, that would be weird. E1. And then it would be equal to now that's the question how it interacts with multiplication. Because depending on how it interacts with multiplication, this could end up a different way. Okay, let me check. Let me double check right now. Is equal to AE. Why? I don't understand this. Why ACE1 is product E1? That makes no sense. It makes no sense. Distributive law for exterior product. What's the distributive law for the exterior product? There's a property. There is no... I swear, I swear, I swear. What is the law? Which product? Now it's called a wedge product all of a sudden. Oh, I swear. I am lost. Great. Where were we? Oh yeah, multi-vector. Great. So this is an exterior product. This is an exterior product. Okay. Vector space V. So exterior algebra then. I still have no idea what that is actually. What's the? I get the exterior product now. The exterior product of which product as its multiplication? Oh, okay, 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 alright. Areas, volumes, their high dimension. Exterior product of vectors in V. No, yeah, it's called a bivector. This is exterior algebra. I am trying to check something, double check something, and I kind of might have ever so slightly fell a bit into a rabbit hole, and well, are you familiar with exterior algebra? Do you by any chance know the classic one? Yeah, you know. Do you know how to distribute exterior product by any chance? I'm just wondering. I'm just wondering how to distribute an exterior product. Alright, anyway, back to the thing. So, this algebra, okay, makes sense. Multi-vector. Alternating means is equal to 0. Is it the alternative? Is it the alternative property we're looking for? Wait. This actually could be relatively reasonable now. Wait, alright. So, for all x and y... Okay, oh my goodness, my brain. So, multilinear map. Alternating, it vanishes whenever two arguments are equal. Because the exterior product of x, exterior product x, is equal to 0. Right? Right? I have no clue. I don't know. I have no idea. Maybe that's the reason. Imply that. Yes, great. Examples not the only example is not the example. Sedanians. Yeah, I know. I know they do. I'm trying to figure out why. Okay, great. Great. Amazing. Wonderful. So, still have no idea what alternativity is. I just know that alternative algebra. So I just have to. I have no idea. Bing. Oh, Bing. That's such a good idea. I forgot Bing is so powerful now. What is alternative algebra? Chat, tell me. Tell me all you know. I forgot how powerful Bing is right now. Oh, yes, gaming. Alright. ChatGPT banned my VPN, so right now I have to use Bing. What does it mean for multiplication to be alternative? Wait, is that right? Yeah, it is. Just literally told me what I... Okay, cool. Alright, so that's it when it comes to alternative algebra. Great, great, no, that's great, cool, cool, cool. So we're one step closer, one step closer. I don't quite get how... Let's check it for ourselves. So, xy is equal to xy. Let's see if quaternions fit that. Alright, great. So, let's do it with j and k. So, j times j k is equal to j k. Cool. So, j times k is equal to I, which means that it will be j times I, which is equal to -1, which is equal to negative k. J times I is equal to negative k. Yes! Oh, yes, that's great. Fantastic. Well, that was a lot of work. Okay, cool. Now, it is worth to mention that this, right? I think. That being also associative. I missed out. Oh yes, so being associative. Being associative means x times y times z. Oh, being associative means... Alright, it's not that complicated actually. Yeah, once you get the general feel for it, it's, yeah, okay, so x times y times z is equal to x times y times z. Okay, cool. Oh, great. And apparently quaternions are associative. That's great. Being... it's fun. That being commutative is not the last stop for being hypercomplex numbers. I guess that's what we could call it. I don't know. I'm losing myself. Okay, great. Not last stop for... I don't know how to put it into words, honestly. My brain is mush at this point. So, that whilst not being commutative, quaternion quaternions are still associative and alternative. Might come in handy later, I don't know, I just wanted to yeah. Worth mentioning that was not being commutative, quaternions are still associative and alternative. Great. It's because first associative, so nope, wrong thing. This copy, yes. Times z, jk, let's do I, why not? X, Y, Z, alright, so it's j times k times I. Because that's equal to yeah, this will also come in later, but first. Alright, great. Now this over here. Nope, nope, not quite what I meant. There we go. J times k, which is equal to what? J times k, which is equal to I. So the right side should be -1, right? So this one should be j then. Because k times I, that's -j. J. No wait, k times I is j. Yeah, I. Right. And j times k is I. Great. Cool. Oh, fudge. This is fun. This is so much fun. I'm having so much fun. You could not even imagine. Now, j times j, that's simple. -1. -1. Great. Oh, fantastic. Fantastic. Now, for this, it's a bit different. Because it's j times j times k, which is equal to j times k. And now this is equal because obviously, right, obviously, j times k is equal to I, and j times j is equal to -1, right? Yeah, -1. -1. Now, obviously, -1 times k, that's just -k. Obviously, and j times I is just -k. Great, cool. Great. Cool, cool. So now that we know that quaternions, right, are not commutative, how can we use that? Well, I mean, oh yeah, what we start with, yeah, the multiplication is not actually always commutative. That's great. But it might be my argument. Now the argument here might be a bit controversial, but I do believe that it's not I believe that we should say no wait I do believe that saying quaternions are not is a bit incorrect. I should say that it's not commutative. It's not commutative. Unless talking about multiplying complex numbers. That's controversial. That's, let's just say that's rather controversial. It's because we can compare it to exponentiation. Whilst exponentiation is not commutative by itself, it can be commutative in some cases. To be exact, now we'll just have to some shenanigans. X to the y is equal to y to the x when... How do we know? Okay, now we have to solve this, which would be a lot of work, and considering that I'm dumb, it would take a lot of time. So instead what we'll do is we'll take the approach for last video, which is consult someone smarter than me. That person smarter than me being obviously Black Pen, Red Pen, very famous YouTuber, very famous mathematician, very great mathematician, one who taught me calculus, actually calculating calculus, right. Okay, but calculating calculus here, Black Pen, Red Pen, looking that. And so, if you'd like to see the actual solution step by step, then go there. Instead, I'll just copy it here shamelessly, because as I said, I'm too afraid I'll mess something up, and if I mess something up, then kind of argument here might fall apart a bit. So it generally looks like this: t to the power of 1 divided by fraction 1 divided by t minus 1, and y being equal to e, right? Yes, t for and t, which is that's, I do believe that's any numbers, right? T is equal to real numbers. I do believe that's, it will be real numbers, right? Where's the real number sign? Real numbers. Could it work with imaginary numbers? I know it couldn't work with... wait, minus 1. It will not work with 1. If you input 1, the whole thing just breaks. It's 1 divided by 0. But imaginary number. This is imaginary, or that's C. It's so fancy written. Natural, real, that has to be. So complex, obviously. Complex. To work with complex numbers. The simplest complex number I can think of. I. Counts as complex, it's 0 plus I. 0 plus I times 1. Alright, so x is equal to I to the power of 1 divided by I minus 1. Yeah, that's calculatable. I mean... Let's consult someone smarter than me, Wolfram Alpha. Alright, great, so we could do just t to the power 1 divided by t minus 1 is equal to the same thing, except no, it's not. Oh fudge, it's actually not. x to the y is equal to y to the x. All the solutions for that. If I can get these. YW! There is... I know YW, but still. I am disappointed. I am disappointed. I am disappointed! We'll have to go with this. I'm present. It's so annoying about complex numbers that there's no decimals for complex numbers. In which I could just... Actually, wait, there is. I'm such an idiot. All hail great GitHub. I've used this to one of my videos a long time ago. So t to the power of fraction, can I... Yes! 1 divided by t minus 1. Graph? Walk? Oh wait, Z. I'm such an idiot. Oh, there we go. Okay, great. So, do you see any gray areas? Because I do not. Oh, that's one. Yes, it won't walk at 1. Well, no, actually, wait. Oh, that's simple. I'm sorry, my brain is mush. I'm not thinking correctly. Obviously, it won't be that simple. What we have is x. Oh my god, tablet just went great. T divided by 1 minus t minus 1, wrong way, t minus 1 is equal to 1 divided by t minus 1, and that's t actually to the power. Great, so now we have that. You can see that x to the power of y is equal to y to the power of x. We could plug these in. To see how it will be solvable. Yes, we could plug this in to see how for what numbers would they be solvable. So t to the power of 1 divided by t minus 1, doing it without a graphical calculator is a pain. No, without graphing tablet. You know, the thing with a pen to draw on your screen. So times t to t. I will get the same thing on both sides. That's the point. Make it, you idiot. Because over here will be t to... I'm such an idiot. Yes, I will get the same... That's the point. Times t to the... Wait, will I? Maybe... I think, yes. But still. Wait, t minus 1. Then what we can do is we can... multiply with this. So over here we'll get t minus 1 to t minus 1. T. Great. And over here we'll get it equal to t minus 1. This will be squared, so it will be to the second minus 1. I think. Oh, it's not equal at all. I messed it up. You get t to t times t. That will be squared. But that will be t to this power. Where I messed up. This is inputted as a full thing. Wolfram alpha. Wolfram alpha. Oh boy, this. Get ready. T to the power of e divided by e minus 1. That's why. This is why. This is why. On the other hand, x would be equal to t to the power of 1 divided by t minus 1. Alright, so now what we do is we do this to this power, which is equal to turn it around, so no! I killed the thing! I killed the poor thing. Muffin input. Yeah, that does look. Yeah, yeah. Oh no, I killed it. No! I need to get pro. I ain't got money for that. I'm already going to be. Yeah, I don't have. That's great. No, that's great. Alright, now. Yeah, no, it has to be 40, and yeah, we have to define T in this case. Yeah, fine, read. Alright, great. So we could also say that x times y is equal to y times x for x and y. X and y in complex numbers. Great! So now we have turned our one problem to two problems. Oh yes, great. Oh, that's fantastic. Now all we have to do is we have to figure out. I mean, this is still better, and we still can say that addition is commutative because it seems that as this is all numbers. Great. So so what now? What now? What now? Well, good question. Now we go back to the drawing boards and actually wait, we can say some stuff. First of all, if we go back to this, we still have those two problems, but we can for a second imagine that we don't have these two problems. That they're already solved. Oh boy, okay. So, actually, might not have two problems. And so there we go. Multiplication is no longer mutative in hyper-operational mathematics. Now it's time to go back our original equation. Just fix it, there we go. Great. This. It's great, not gonna lie, it's great, it's kind of great, it's, well, it's okay. Ah, by the way, this should be in brackets. The ends should be in brackets. Make this more readable, great. Alright. Cool. Negative number in here is obviously -1. Which means that it works for subtraction, works for division. It doesn't actually work for... Alright. So let's first address the elephant in the room. Subtraction is fine. Because A down arrow B is equal to A up arrow B, B up arrow at N. Division is fine. This is division. And that's correct. A times like this. But what is the anti-operation of exponent? That's a good question. Ha! Yeah, so now... That's a very good question. Well... I think we can define it very neatly. Oh, wait. Oh, I think we can define it very neatly. In order to answer that question, let's see what can we achieve with the anti-operations. For this, we'll need this. Okay, great. Is equal to 0. Down arrow. Will be 1. Nope. 1, 1, 1, 1. What are these anti-operations? I've written it 3 different times, 3 times differently. Let's ask another question. What are these? What is the music, by the way? Out of the Rain, that is Fat Rat, but that seems that I think that's the newest song. Also, I have nothing with this one. I should probably change the music because I don't want to be stealing the new songs. Let's. Alright. These anti-operations returning when operated on the same number. Yeah, I should probably just do A. Now there seems to be no pattern there. I hate the fact that we did it only twice and I'm already saying there seems to be no pattern there, but I would do it the 3rd time if not for the fact that we don't actually know what is the anti-operation of exponentiation. Actually, we may know. Wait. A down arrow B, up arrow B would be just A. Which means A up arrow B, down arrow B should be equal to A. Which means what we are looking for, that would be a root. Yes. So these are roots. What about roots? Yes. A question. Let's ask 2 more questions. Two more questions. This will be actually the second one. There we go. This one will be, are these really anti-operations? Definition of anti-operation is on the right. Well, in operations, order to, if these will not be anti-operations, I will flip. I just want to tell you that. Check. Let's check. Let's solve. Equate. Check in order to see if these are really anti-operations. We will need to operate with operation and anti-operations and check if they cancel out. Great. Expected is, I don't like the fact that I'm rewriting expected. That means that the actual will be different. if this will be different, then oh my goodness, I will be in a lot of trouble. I think I might have to drop it. Fudge. Oh, expected calculation. Please be real. Is equal to, over here what we need to do is we need to use this equation. Actually we should do probably with you know, more general equation with n, down arrow, up arrow. Okay, great, is equal to a, which means over here that this is up arrow n plus 1. And then up arrow A. Great! Which means that first, there's a lot going on here. You know, check that. It's kind of hard because we cannot really divide by both sides like a normal math. We can't. We simply cannot. Because, well, division is not actually proven to cancel out things yet. So, I guess we could also do... by contradiction? Might be easier, so we basically would say that these do cancel each other out, then could say that these do cancel each other out, and then they'll just this is equal to what? What then? Next. Well, the order does matter. Order really matters in this case. We are going from the left to the right. Order matters. Kind of giving up. I don't know how to prove this. I made up this math. I shouldn't be able to prove it. Well, I did, and this is a fraud experiment. Sometimes, by the way, it should be here. We could use an actual number for this. Instead of b, we could use 2. We could, wait. We could use 2 for this. Because we know a property of 2. Also 3 or whatever. We know that we could break it down. Alright, let's try to break it down. Which is equal to... By the way, I'm pretty certain this will just go on. Yeah, so we'll have to enter here. Which would be equal to A. Copy this. This. But we can break down the last part, right? we can break down the last part as being up n minus 1. It's going down should all the same way, right? B, okay. So a to the power of b, for example, can be considered as a times a times a, b times a times b could be considered a plus a plus a times, which means it's operation 1 less than b times. Operation 1 less on a but the whole operation b times. So this operation up arrow b times. Does that help? We need plus 1, so it does not. Proof by contradiction would be so much easier here, I think. But we don't have anything to contradict. I should introduce this as an axiom, honestly, at this point, because we are just lacking necessary tools to prove anything. This entire calculation is an absolute mess. Just... Continued. For now, let's button there, but there is a pattern. Also for on itself. Oh, it doesn't work for roots. Does it? No. Because roots don't walk. Roots are... Yeah, for powers, these are not roots. These are not roots for powers. I mean, by definition, for powers, these wouldn't be roots. So A... its quote-unquote root, not actual root, should be equal to a to the power of b tetrated by -1. Now tetration by -1 is problematic. Why? Because that's 0. I love capture. I am barely holding on. Trying to invent more. Oh, it's been 2 hours. Oh, it feels like 15 minutes, honestly. The thing that we are missing mostly we also would have to assume as an axiom that anti-operations exist. Let's ask another question. What do these operations return when operated on the same number. Alright, we'll have to add another axiom, sorry. I'm very sorry. Commutative and addition and anti-addition. Down, arrow. It's truly cool commutative. I think it shouldn't be said that it's commutative actually. I think this might be a bit misleading, considering that multiplication, well, to be fair actually, down arrow, where is it? This is inside it. Down arrow. Commutative and and it is also, what would be the word? Can be reversed with anti-addition. Addition. Actually, no, wait, yeah. Just first with anti-addition, so that A up arrow B down arrow B is equal to A. Great. Now evolution axiom. We can drive through based on the underlying true base operations, and that each hyper operation has its own anti-hyper operation. Down arrow and whatever. Okay, so anti-operation. Okay, great. Cool. So now that we know that, what about anti-exponents? Because these are not roots. That's what's crazy. They're not roots. Probably not roots. Yes, because the hyper operations will have this very neat thing. There's a pattern. Anti-operations when operated on themselves return a fixed point for a given hyper operation. I can prove that! If I go the other way, I can prove it. Actually, no, wait. I can also go this way. We can prove this fact based on the... that's so awesome! Based on the evolution axiom. No, wait, based on the... what's the first axiom? The first axiom. Operations axiom. Oh, that's so awesome. We can prove that. We can actually prove that. Which states that addition. Actually, no, we do need to Actually, wait, we can leave it here. Evolution. Which, when applied, can reverse a given hyper operation. For example, there we go. Come on, why what? No, like this, there we go. For example, this. Appropriation, this, and it should be up arrow N, down arrow N. Oh, that's so sick. Based on the evolution axiom. Evolution axiom, which states that what is it? What is it? Yep. Each operation can reverse the given hyper operation. There it is. Bold. In italics. Which means that up arrow and B, down arrow N. We also would need to give an axiom that is equal to A up arrow. Okay, fixed point. Fixed point will be denoted by something that's it's tempting to use capital pi or psi. Fixed point. Is there generally some sort of thing that could help us, you know, just say fixed point? These are angles. No, that's too funky. Let's just keep it. Actually, I do hat F, which means that where F at F is a fixed point. Actually, we have to modify that. I'm sorry. There we go. Fixed point for a given hyper operation. Now this is great. This is great because that means that whilst roots technically, yes, this may seem as if roots like well, here's the thing. Okay, give me a second. I need a second to calm myself down because this is just awesome news. It means that roots are not anti-exponentials, but they are very close. They are very close. In order for something to be anti-hyperoperation, it has to satisfy these two things. First one of them is that they reverse the equation, which is correct for exponents. No, if you have a to the second power with second square root, it is equal to a. Great, good job. Yes, done. Basically, a b is equal to a, but only sometimes. Here's the kicker. If a is negative and b is if B is even, then this will be equal to... If A is negative and B is even, then this will be equal to negative A. Mind blown! Which means it does not always work. And because of that, but we can detect it doesn't work with the second thing. When we have some number B, when we have some number, B to root of B, it's not always the same. 2 to the second, I can show you that actually. Much better way. Desmos! Gaming! Yes! It would be basically root, actually square root, so I do believe it just works. Root, alright, we'll do the bottom way. 1 divided by x! See? These are not the root, because, and we can detect it in 3 different ways. Which is awesome. Now, based on what I have said so far, we can make argument that roots are not exponentials based... No, fine. Exponentials base... We can prove these are not actually in 3 different ways, which is insane. First one, which is that to be fair, we are only working with positive numbers, but work. Yeah, it still would work with actually negative. Yeah, it still works. Here's the thing. Oh, it's so awesome. Equality. Oh, but that's just square root, normal square root, boring. This n to the n is not equal to a constant. That's first. Second, which is that it's just not equal to a constant. Second is that let me just copy this. This to the power of n, it should be a to the power of b. So I just still did n, I missed. Is not equal that's actually correct. Is not equal to a if a is... Oh, that's so... feels so sick. Feels so sick to prove that in this field, roots are not the opposite of exponents, which is amazing. To the negative numbers. Is there for negative numbers thing the magic? Where did I find the last one? This is negative, right? Negative real complex. Negative. Let me check. Negative numbers. Got the symbol. Symbol. There we go. Natural numbers, not quite in front of the number. No. No. This Wikipedia has to have it. Every user. numbers. I forgot what is the dot 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 of all negative numbers. Natural numbers, that's n. Rational numbers, that's q. But negative numbers, that's not. It has a freaking thermometer in the. As well. Natural numbers. Just. Rational numbers, real numbers, complex number combinations. There is no for only negative, really. Number Z-minus. So you just add a minus to it. Okay, thank you so very much. So just minus, like this. Right? As an exponent. Wait, as an exponent? So like this? And b is equal to 2n. What's your set? My set? Well, natural, right? No, real. You are right. You are so very right. This should be real. Yeah. If a the real negative real numbers. Yeah, negative real numbers. I not mistyped, not missaid, not miss. I missed. I missed the thing. But yeah, and now that's the second argument for why roots are not anti-exponents, and the third one. Wait, this arrow shouldn't be here. All right, the third one. That was my train of thought. What was the third argument? There was a third argument. Oh yeah, based on this. Yup. Is equal to A up arrow. So that's the power of B 1, 2, 3, 4, -1, which is equal to A the power of 0, which is equal to 1. Which is contradiction, because you know that would mean that, yeah. Wait, no, that's the wrong. Oh yeah, that's the wrong thing. Yes, that's the wrong thing. My goodness, my brain is smushed. That was the third one. I forgot what it is. It was a third definition. I forgot the third definition. I had it just a second ago. Maybe it was based on the constants. I mean the fixed points. But it already says over here that there is no fixed point for this. Well, now let's say that 2 because I forgot the third way, so whoops. So now what we need is now the fixed point for exponents is 1. We know that. Yes, it is 1. Because basically a fixed point of operation, right? Let's also expand the when operating any number by any number on the appropriate fixed point, original number will be returned. So for example, a up arrow is not that's the okay, but I mean I don't know if there is no other symbol here. Actually wait, oh my goodness, my brain is remerged. Thank you for being here. Okay, LaTeX, listen, mate. How do you reel? Yeah, I know, I'm sorry. Mav BB. Cool. So the function mav BB. Capital 2. Absolutely does not work here. Isn't there a better way to do it? A different way, by any chance? Perchance. Real. RE. Great. Got it. Understood. There we go. No, that is... Yeah, as I said. Yeah, there's just no different symbol. Unless... Missed. No, this is a different real. Never mind. Nah. But there's no way to actually do the real. Unless... Absolutely not. Real? Absolutely not. Google Docs. Unicode character. But that's an equation. I don't know if I can maybe I can Unicode real numbers. Double strike capital R. Yes. No, I need if convenient. It does work, you are right. I'm pretty certain it does not. Double strike. Double strike. C. Wait, is it C? No, Z. I'm such an idiot. My goodness. Fudge. Z. Right? Wait, is it Z? Now I'm doubting myself. It is Z. Where's my... which one? Which tab has... No, that's Kelly Dixon. That's... this was... That's... There it is. Number. Yes. Complex... No, it is C. Never mind. This time. Alright. So now... Now great, now all we need to do is find the actual anti-exponentiation that will fit... Yeah, that will work on everything. That will have the actual thing. And considering that in real math, I don't actually know if there is a function like this. I don't think there's an operation which would work here. Because of how interesting exponents are. Because -1 times -1 is equal to 1, which means we would need an operation which could somehow know. Is usually used constant. I mean, normally C is a constant, but I do want to make sure that it is that is obvious as not a variable. Alright. The problem, I don't know if an operation like this could exist. I don't think, I mean, we would need to do some real rule bending there to make it happen. I don't know if it could exist, because here's the thing: in order for an operation like this to exist, you would have to take a number, positive number, and figure out whenever it was originally a negative or a positive number. Now, existence of... I mean, here's the thing, we can't in normal math. The good thing about this is that this is a thought experiment, which means this is not normal math, which means we can dictate the rules, which means we can say that our operation knows, for example, or something like that. Now, existence of an appropriate anti-exponents operation in real math is problematic at best. It's because when you have a positive number, C, you would have to know whenever that number originated as a positive number or a negative number, which in conventional mathematics is just madness. I mean, it is. But fortunately, we are not working with conventional mathematics, so we can say that numbers contain both. This is very controversial at this point. At this point, this is absolutely not math. This is far away from math. Both the value and the original state. I cannot stress enough just how little sense this would make in actual math. So just in mind that this is a thought experiment. Yes. Actually, let's give my this experiment. Great. Oh, so now What nice argument, make it. Why did you back it up with a source? I am the source! Okay, cool. I wanted to say it for a really long time. Great, great, it's fun, it's fun. Not gonna lie, it's fun. This is, by the way, the 7th page. Only the 7th page. We're getting there. Right now, what we basically mentioned is that these are super roots, basically. These are very powerful roots. These are super roots. Super root. Oh my goodness, my hand. Listen, I'm writing with a mouse, so yeah. These are basically ultra powerful hyper roots. No, not hyper, super roots. Hyper means something different there. So, by the way, funny story. Normal definition of absolute value of x is obviously root of x squared. But in hyper-representational mathematics, this doesn't work, so that's fun. Because there are no roots, and there are only super roots, which means that if you put -2 here, -2 would get squared. This is a super root, so we'll have 2 lines, whatever. This notation is not canon, by the way. This is actual canon notation for super root. And it's also named super root, it's also not canon. Now, which would mean that this would be this root of -2 actually, or 4 actually, I can do math, easy, 4, which then will be equal back to -2. Wow, that's actually, I like it. It's weird, and because of that I like it, it's different. May not be useful, but you know, this is not design. I'm a YouTuber, right? Nothing I do is designed to be useful. Great! Oh, my goodness, 9 PM! Wow, it's been a while. I've been having a blast. Oh, I uploaded the second shot and it didn't perform well because it's about charity. Who would have thought? Am I right? I think I'm gonna die in the pit. Goodbye. Don't worry. I'll be joining you soon in the pit. That is fun. So that means it's not actually, yeah, it means it's not commutative. Yeah, that's just my graphics. I wouldn't mind that. So so this is not a rule, not commutative. It can be commutative in some cases, but that is not a rule. Can be commutative, but some cases, but not every case is defined as commutative. This is very fun. Wow. C, A, B is equal to A, B, C is equal to A, B, C is equal to C. No value difference. Also, we wouldn't have to add to the numbers axiom that numbers carry additional information. That's insane. The more I say it, the more insane it sounds, but it just doesn't stop getting insane. Anyway, I think it's time for me to end the stream. We did a lot. We did a lot. We broke math. Oh, this would be such a great clickbait video. We broke math! Question mark, question mark, question mark. I can see it happen already on the big screen. 4K! Anyway, that'll be it. Thank you, Elliot, for being here. And Elliot only, let's be real. Elliot is the only person in the world. I hope that one day hyper-operational mathematics would find a use. I'm hoping that one day someone could find a use for hyper-operational mathematics, because that would be fun. That would mean that there's actually goal to it. The good thing is that worst case scenario, it will just be useless, which means there is no harm in trying. There is no harm in trying. If I said that this is true, that would be harmful, but I'm not saying this is true. I'm saying might be and it might not be. There's no way to know right now, so it should be. So first thought should be it's not useful, but there is no harm in trying. That's my opinion. So yeah, fun thought experiment. Anyway, that'll be it. Thank you everyone so much for watching, and have a great day. Bye.